Hi, and welcome to part 3 of the Sound Basics. Today we're going to talk about transducers. So speakers, microphones, record players, and of course the ear. So let's start with our friends at Imagination Station here, channel 13. They're going to talk a little bit about how a speaker works.
We're talking about sound. I mean, you've probably heard about Apple and Beats and the headphone thing and all that.
Right.
And it got me thinking about how, whether it's headphones or earbuds or ginormous speakers like this, they all work on the same basic science.
Ginormous is a scientific term.
It is, absolutely. So this is a medium-sized ginormous speaker here that I've cut apart and removed the cone from, okay?
Right.
Because the way speakers work is there's a permanent magnet on the back. That's the thing that, might stick to your refrigerator. And there's a tiny, tiny little coil inside. This is an electromagnet. Okay, that little gold, that coppery stuff there. That's what we send the signal through. The current flows through that, turns it into an electromagnet that'll either attract or repel, probably this way, attract or repel to the permanent magnet.
Now, I'm sort of having flashbacks here because it doesn't seem like speakers have advanced all that much since the 70s
Hey,
or
if
60s.
it works, don't mess with it, right?
Yeah,
so,
I guess not.
okay, so Tony, go ahead and grab this. A
right.
big battery here, and we're going to send some current through this speaker. And if we just sort of, we can make it repel or we can make it attract. Okay, so if we send a current through that electromagnet, it'll move up and down. It's probably hard to see, so that's why I brought the balls here to throw on top. And so if we do this, you can hear the sound as the model air molecules move back and forth, right? And that's basically how a speaker works. Now, I thought, that's kind of cool, but let's have you make the world's simplest speaker in like 10 seconds.
Oh, sure.
Okay? So I got a piece of cardboard here. Go ahead and hold the cardboard.
Got it?
Piece of copper foil. In fact, I'll hold the cardboard. You peel the adhesive backing off.
Will do.
Okay, don't let it curl up on itself. I want you to lay down a straight line on this piece of cardboard.
I'll try. All the way
help.
across, right?
Yep.
Does it matter in
Doesn't
which direction?
matter what. Yeah, this looks like
Okay.
a good direction right there.
So you can do this with your
Perfect.
graduation cap today, folks.
You probably could. Look at that. This is a speaker. Although, we're missing a couple things, right? One, I need you to hold this really, really strong magnet. I have connected up my iPhone to an amplifier and then also to these wires, which are connected to this coil.
Okay.
So I'm going to start playing some music, and you probably can't hear anything because we need the current to interact with the magnet. So bring the magnet a little bit closer.
Does it matter which side?
No.
Yeah?
Can you hear that? It's really kind of faint.
Yeah.
So it's really hard to see. What's happening is the current in here is attracting and repelling against that magnet, and it's causing the whole piece of cardboard to vibrate. So let's step it up one more notch. I made a more elaborate version
Oh,
of
look at that.
I wanted you to have fun actually making one, though. But now this one is just a really big, flat coil. So bring the magnet closer to this one.
All right. Wow.
Really close.
Definitely can hear that. Wow, I can feel the pulsating as well.
You can
Yeah.
feel- so go ahead and move it around. So depending on where you put the magnet, or if we take it away, it comes back.
Nice.
It's amazing how well that works with
That
just
is
a
cool.
little coil of copper on the paper.
And you have to make a fun design, too.
Well, and what this does is actually sort of concentrates the magnetic field, much like the coil inside the speaker, so that it gets stronger, so we can have better interaction with the magnetic field from the permanent magnet.
Wow, that's cool. And it's entertaining as well.
Right, so, this is basically how a speaker works. Basically, sound that travels to your speaker, like from your iPhone or something like that, is just really electricity, all right? And what we use to convert the electronic energy into mechanical energy, which is what a sound is, right? As a sound wave is, in fact, changes in pressure, it's mechanical energy. We use a transducer, which a speaker is, for example, a type of transducer. Let's see. Right. So what happens here is you have a permanent magnet, as the gentleman was saying in the other video, and then you have an electromagnet here. All right. And what the audio signal, and again, audio signal is just electricity, but it's alternating current, right? So it's oscillating back between plus and minus, plus and minus. So if I'm sure you've played with the magnets before. If you turn it to one side, the magnets attract to each other, and if you turn around one of the magnets, they repel from each other. And that's essentially what the electromagnet is doing. It's in one direction, it's being repelled away from the permanent magnet, and in another direction, it's being attracted to. And so this alternating current is changing the polarity of this electromagnet back and forth, back and forth. So you get that kind of oscillation. So if you have an oscillation here in the electric current that matches the oscillation in air pressure, you're going to get yourself sound, right? And so then this coil here is attached to something that'll push the air a little bit better, a cone, and then it has a little suspension there. And then it's making sound waves, right? So the cone pushes the air, translating that electrical energy into mechanical energy, right? And then hitting our eardrum. There you go. So we can also look at the record player, another transducer, and in this case, we're actually trying to play back some sound. And again, the principle is the same. You have some kind of oscillation, and if you capture that oscillation, you can capture that change of compression or rarefaction in some way. Then you can play it back, right? So this is how a record player works. It has this little stylus, right? And then it has these microscopic grooves in the record, and it pushes the stylus back and forth, right? Pushes it back and forth, and then here you have a little magnetic coil, and it's translating that mechanical energy, which is captured in the groove, into electronic energy, which is generating by this magnetic coil. The fluctuations in this little magnetic coil is changes in electricity. Okay, let's see, yeah. Right, and I mean, I guess you can look at like the electric guitar too. It's the same kind of principle. Well, we won't look at the electric guitar today. All right, so that's how this is the basic idea of a transducer, of transduction, changing mechanical energy in this case to electrical energy, or in the case of our speaker, changing electrical energy into mechanical energy. All right, so let's look a little bit at how a microphone works. It's very similar. We'll watch this video here.
How do microphones work? Though they have their differences and different uses, they are all transducers, converting sound waves to an electrical signal. The dynamic microphone is the most common used. These work using electromagnetic induction. Sound waves hit a thin diaphragm, which causes it to move. This diaphragm is attached to a coil surrounded by a magnet. This magnet creates a magnetic field around the coil. The sound waves hitting the diaphragm are moving the coil, and the coil's movement past the magnet creates an electrical current. This electrical current is your sound signal. Loudspeakers work in reverse. Here the incoming sound signal moves the coil, which in turn moves the diaphragm, creating sound waves.
Right. So, yeah. So this is this basic method of transduction, right? You have this electromagnetic induction through a diaphragm. The air pressure hits the diaphragm, is very sensitive to changes in air pressure, and then it moves this coil back and forth. So like the reverse of the speaker, it's creating an electrical signal. It's a basically, again, like an electromagnet surrounding a permanent magnet, and as it oscillates back and forth, it's generating that alternating current going from positive to negative, negative to positive, right? And it's capturing that in an electrical signal. And of course, we can record that electrical signal. We can capture that, and then that's like our recording. And again, just as we saw before, the speaker works the same way in reverse, right? All right. So that's a microphone. And finally, let's have a look at the ear, which is, our natural transducer, and a really very sophisticated one, very interesting. But in a lot of ways, the human ear is basically like a pump. It's just a mechanical device, really, and then it creates these electrical signals, which is then sent to our brain. So let's have a good look at the anatomy of the ear.
Many of us take for granted a very extraordinary organ, our ears. To understand the ear, we need to understand what sound is. The speakers you are listening to right now are vibrating, flexing in and out, causing a wave of pressure through the air. The frequency of these waves, or the speed at which the sound creating surface moves back and forth, affects the pitch of the sound. The level of air pressure in each wave is directly related to how loud the sound is. The outer part of our ear catches these waves. It faces forward and has a specially designed structure of curves helping us to determine direction of sound and emphasize frequencies needed for human speech. Now that the sound waves are caught, they travel through the ear canal and strike against our eardrum, a thin membrane about 10 millimeters wide. Now that we receive the sound, the middle ear transfers this energy. The smallest bones in your body, the malleus, incus, and stapes, start in motion. The malleus is attached to the eardrum, and as the sound passes along, the force is amplified by leverage until it arrives at the stapes, which acts like a piston, creating waves through the fluid of the inner ear. The most significant increase in force comes from a system of hydraulic amplification. The face of the stapes has a surface area of 3.2 square millimeters, while the eardrum has a surface of 55 square millimeters. Using this, along with a leverage through the malleus and incus, the final pressure is 22 times greater than when the sound first arrived. Now, we arrived at the most complicated part of the hearing, the cochlea. In reality, it is coiled up, but it is easy to understand straightened out. The stapes is causing pressure waves to travel through this structure. Along the inside wall is about 20 to 30,000 reed-like fibers. As the waves move along, it encounters fibers with the correct resonant frequency and energy is released. These fibers are not actually what give the signal to us that we heard something. There's a special structure containing hair cells next to these fibers. When the fibers resonate, they cause the hair cells to move, which then sends an electrical impulse to the cochlear nerve and on to the brain. Certain pitches of sound will resonate in specific locations, and louder sounds will cause more hair cells to move. Our brain interprets all this raw data, making it possible to enjoy a beautiful song or a conversation with a loved one. Just to think that all this is happening in your head right now at full speed. And not just one, but two of these sophisticated instruments are helping you to have the amazing sense of hearing. This is just one of the many systems found in the human body that go far beyond our humble human understanding.
So if we look at this animation here, we can kind of go through some of the steps here. We have this eardrum, or tympanic membrane, and it's this kind of flexible membrane that's connected to these three bones, the malleus, incus, and the stapes, right? And it's moving them back and forth, and then this is pushing on here, this oval window, and then moving the fluid. So the cochlea here, this curled up snail-like thing, is actually filled with fluid. Okay. So you see the sound waves there, and see, it's just really like a little pump. It's causing changes in this fluid. It's pumping. Now, just as in the other video they mentioned, these bones serve as really an amplifier. So you get the leverage here, right? Because you're pushing on this end, and the force is coming through this end. So just like it's the length, right? And then also you get the amplification, because this is so much of a larger space and this is so much of a smaller. So the power gets amplified through these three bones, the smallest bones in our body, right? And then these are actually openings here. And they're just covered with a membrane so the fluid doesn't leak out, right? So this pushes there, the round window and the oval window, and pushes on that fluid inside the cochlea, okay, at the rate of the sound coming in. So again, here's another transducer. It's taking this mechanical energy and putting it through a couple different steps, amplifying it, changing the medium here, becoming the fluid. And then if we look back at the other video, it then changes into electrical signals here in this area here, okay, in the cochlea. So this is the cochlea spread out. Basically, what's known as the place theory of hearing is that different kind of waveforms, it's a fixed space. It's just like a bathtub or something like that, you know, a nice tube filled with water. And depending on what kind of wave comes through, it's going to bounce. And we're going to talk about standing waves in the next section, but it's going to bounce back and forth, and there's going to be areas of excitement just like in the air, and areas of rarefaction, compression, areas that are excited and areas that aren't. Okay, and so basically it's going to excite one place in the cochlea. So a certain sound wave, let's say it's the A on a violin, is going to actually stimulate a certain area of hairs. Okay, because it goes back and forth through this column, and only certain areas are activated, right? And so
The inside wall.
it's going to stimulate. It's going to stimulate one part of the cochlea, these cells here, which then in turn stimulate these little hair cells, and they create electrical energy into our brain. The moving back and forth of the hair cells turn into electricity for our brain. All right. Again, a transducer, pretty simple kind of thing, but it's really, really accurate, and it's pretty amazing the amount of information that can come by such a simple mechanism. All right, so that was the basic transducers that we're going to deal with in sound: speakers, microphones. I guess we don't use record players so much anymore, and the ear. And again, this is a kind of a crucial principle in hearing and sound, is that in order to have recordings, in order to play things from our iPhones, or even to get sound into our brains, we have to go through this process of transduction, of changing mechanical energy into electrical energy, or vice versa. All right, so please join us for part 4 when we start delving into resonance and modes of resonance.